Look quickly, a little bit about me for those that don't know me. With R.E.Y. Engineers in Folsom, licensed up and down the West Coast. Spent most of my career with CH2M Hill in several states. My career started in 1979, and about the first technology I was exposed to was the tellurimeter, that microwave instrument you see on the right, which was just an amazing piece of equipment in the day. Could be 10 miles apart, not even seeing the receiver at the other end, and actually talk to the fellow operating the receiving unit on the other end. The smaller cones were capable of about 10 kilometers. I believe that long cone attachment would extend the range of that specific tellurimeter model to about 30 kilometers, I believe. So we'd measure the distance work with the tellurimeter, doing cadastral survey work up on South Fork Mountain of Trinity County and up near the Trinity Alps in northern Trinity County, where I grew up. Turned angles with the Kern DKM2, measured with the tellurimeter, and then started doing transit and chain work for marking and posting projects. First calculator I was exposed to in terms of a programmable calculator was the HP97. It was a great piece of equipment at the time, and it was programmed via these cards that you'd program each card, and you'd have duplicates because they do wear out and they lose their magnetism. So you usually carry duplicates of the same program in your little case. Again, R.E.Y. Engineers is a firm. We're based out of Folsom. We have 15 licensed surveyors on staff. We've been operating the same Regal VMX mobile LiDAR system since 2010, and since then we've been providing statewide mobile LiDAR services to the Iowa DOT for probably 7 or 8 of those years. We also were on an Atkins-led team for providing mobile LiDAR to the Nevada DOT. Being a somewhat early adopter of mobile LiDAR, at least in terms of the survey grade sensor we have right now, which again, it's 10 years old and it's still state of the art. The only place it probably lacks is it only sends out 600,000 pulses per second, where competing systems are doing 1.2 million points per second. But as I'll show you later in the presentation, 1.2 or 600,000, I mean, it doesn't matter. You're going to get the density you need. We've shipped the scanner to Western Australia for iron ore stockpile quantity surveys. Done a couple projects up in Alaska, one transportation and one a sediment project on the Colat River. And again, Iowa's just riddled with projects. We've been out there so many times, and then of course up and down the state of California. A couple of our signature wins, like I say, all qualifications-based selections with the state of Iowa. We're pretty much at the end of our 3rd contract, and I don't know that we will have the opportunity to renew with them. What we did is brought on a local sub to provide local logistics, ground control, be our feet on the ground before we got our system on site. And they bought one of the new Regal scanners with the 1.2 million pulses per second capacity. So we'll be in a support role to them now, but they'll probably take the lead on providing the acquisition for the Iowa DOT. Again, we teamed with Mike Bailey at Atkins a few years back. One of the 2 awarded mobile LiDAR contracts with the Nevada DOT. We did a couple projects on the east side of Lake Tahoe, pretty challenging. Kingsbury Grade, Spooner Summit, some twisty roads. The data came out looking great. Really nice projects. It was good to work with. Continue working with Atkins in the Nevada DOT. But our first client with our mobile system was Caltrans. Our first couple projects were up on Siskiyou Summit, Then we did a couple down, 15-mile project on the Grapevine, a 15-mile project down near Magic Mountain. What a contrast in climate, in geography, and everything, going from Siskiyou Summit up near the Oregon border down to the Los Angeles area. One thing that is really enjoyable about working on the Caltrans projects for us is the ability to tap into the COZEEP and MAZEEP program that exists between the CHP and Caltrans. In this picture you see on the screen, the CHP cruisers are holding traffic back, basically a rolling traffic brake. As you see the cruiser coming up the ramp, as soon as he gets up on the main line, he'll jet around the scan vehicle, get up to the next ramp, get in place to hold traffic until we pass. What this does for us is just gives us a clear picture of the entire roadway, no obstructions from vehicles. As you can imagine, if we were scanning at 50 miles an hour and say a big rig was either going 55 or 45, they would block up to 400 feet of roadway, of that side of the roadway view from the scanner. So it's so nice to have this option on Caltrans projects, both from a safety standpoint and just getting pure scan data to work with. We've done a lot with the Caltrans Chapter 15 mobile LiDAR specification in terms of achieving pavement grade data on pavement. It all boils down to getting the right amount of control, and then scan data redundancy. This graphic out of the survey manual shows overlap area. Well, on each of these projects, whether it was the roadway above, direction, multi-lane in the same direction, or opposing directions on a 2-lane highway, we'll scan each roadway each direction at least twice. On a 2-lane state highway, twice in each direction. On an interstate, we probably take we'll count the number of lanes in each direction. Say it's a 4-lane northbound, we'll drive that at least 3 times. Redundancy is the key to a good cloud-to-cloud adjustment, which without a good cloud-to-cloud adjustment, going the next step to locking it down to ground control, you probably would see residuals between the targets that you would not want to see in the data. In doing the reporting on this type of approach with the sufficient amount of control that in this case Caltrans requires, and the redundant passes, the cloud matching, running iterations of cloud-to-cloud matching, and then locking that resulting point cloud to ground control, we're able to produce a point cloud that's got some amazing accuracies, at least when it's tested at the control point. And with control point spacing of about 500 feet with the vertical, we don't see much variation from the mean that we're seeing in this accuracy report. Our largest project was a huge design build a couple years ago down Riverside County with was the Riverside County Transportation Commission project. Towel brought us in to infill with mobile LiDAR, infill inside their aerial mapping product. Huge project. The green, what you see in the green are only the trajectories we drove the first night. We drove 4 consecutive nights. That's the second night. Third night, we're starting to get into local streets, and then the 4th night. So 4 nights worth of driving, about, that's the entire point cloud. Almost 6 billion points were acquired. We drove about 270 miles to acquire all that data. Again, a lot of redundancy in the driving. 6 billion points were not needed to do the design mapping for this project, but that was the end result of the redundant passes. Basically, we filter that down to a usable file size per tile. So getting into the technology a little bit, mobile LiDAR mobile terrestrial laser scanning, terrestrial mobile LiDAR, mobile mapping. It goes by a few names. We just go by MTLS here in California. Basically uses laser scanners, GNSS system, inertial navigation system, and a DMI that's all attached. All this coming together in a, actually, yeah, there we go. There's some that's one of the two scanners we use, the GNSS system, of course, the IMU and the POS system. The DMI connects to the rear wheel, counts revolutions of the wheel. We measure the wheel diameter, and it's kind of a QC check on the INS. Digital cameras. There can be an array of cameras, up to 6 or 8 cameras plus a video at any given time. And then the control unit, the Linux box that stores imagery, scan data, trajectory, positioning. That's the heart of the system right there. That's what it looks like mounted on our scan vehicle. Again, that scanner is 10 years old and it looks like it's brand new. Operates like it's brand new. In fact, we get it dialed into the point after a certain number of projects over the course of 2 years that we have it exactly where we want it. But then it's time to send it to Austria for maintenance and calibration. And so every time it's come back, we've had to do a new calibration. The factory, I mean, they do great work, but not as good as we're accustomed to seeing out of our own data. So we will typically adjust the matrices to fit what we're doing. One thing that's nice about the Regal VMX systems that they're not modular. We can pick this up, drop it in a Pelican crate, ship it to a project, erect it on a rental vehicle. No bore sighting, no calibration. It's all in place. We only have to have it checked or redone every 2 years.
Hey Joe, just to clarify for the, if you jump back real quick to that last slide, clarify that about the matrices. You're talking about the orientation of the scan heads and the GPS receivers, the antennas, and the IMU, having everything in a mathematical relationship that you guys have to readjust their position after everything's taken off and sent in for service and comes back, right? Exactly.
There's the matrices basically ties each scanner, the GPS receiver, to a point within the scan unit, which is where the trajectory is generated. It's the point at which all of the accelerometers, the gyroscopes, GPS, all those elements come together and develop a position at a moment in time. And then based on the attitude, the roll, pitch, and heading, those, in addition to the matrices, the offsets between the point of trajectory, the scan heads tilt and cant, all of that information comes together. It pulls raw scan data, and based on timestamps for each laser pulse, knows where to place that pulse in space, just based initially on the raw trajectory. And then, as I said, we do cloud matching, which refines the trajectory, and then we tie the scan data to the ground control points, which further refines the trajectory. The scan data is the same, it's just treated differently based on the matrices, the roll, pitch, heading, and the new trajectory position.
Great, thank you.
Benefits of mobile LiDAR, mostly, in my opinion, would be the safety aspect. There is a need to put boots on the ground to establish ground control, but their time on the ground is minimal compared to TSS surveying. We can scan at night. We prefer scanning at night. Occasionally we have a requirement for imagery to colorize the point cloud. Scanning at night gives us we get better positioning from GNSS. We have lower traffic, and it's a better solution. We get a better solution out of nighttime scanning. Time savings, yeah, there could be time savings primarily in the field, depending on the level of detail in the office. You know, you're going to be spending time in the office drawing the mapping from a point cloud, or you spend that time with boots on the ground. So there is a time savings. And again, cost savings, a lot of times it depends on the site. A lot of times it definitely depends on the length of the project. There's a minimum size that we try to focus on where it doesn't make sense to do a mobile scan unless, you know, safety is an overriding feature in which we need to accommodate. And then we will do smaller projects with mobile LiDAR. Again, our scanner puts out 600,000 pulses per second. Show you a little bit more about that later. And then with each pulse is capable of 10 or more returns, in that it's penetrating vegetation. If a laser pulse catches the edge of a leaf and can continue on and hit another leaf, well, we're going to get returns on both of those leaves. Typically, last return we feel is our best opportunity at bare earth. However, on fill slopes where grasses are a little on the tall side, we do not get very good results, bare earth results whatsoever on a fill slope with grass cover. Grasses are pretty solid if you're trying to look through them, and we rarely hit bare earth on a fill slope. Cut slope, we're looking right at the slope with the scanners, just slaughter the hillside. Even with in some cases, if there are grasses, it's all about perspective and grazing angle of the pulse itself. Accuracy, we can ratchet accuracy down to survey grade at highway speed. I say highway speed. We like to stick around 45 miles an hour. Gives us about 3.5 inches between the scan lines. And if you look at the background of all these slides, the background's the same. Those are basically, that's the scan line pattern from the two scan heads that are opposed to each other at about 30 degrees. So we like to keep those about 3 to 4 inch spacing, and 40 to 45 miles an hour is just about the sweet spot for speed and density of the scan data. But there are limitations, as I mentioned, on the fill slopes with grasses and vegetation. So line of sight's huge. Cars, people, signs are all. It's basically what we tell clients from time to time is, if you jump into Street View on Google Earth and pan around, what the Street View camera sees is what the scanner is going to see. They're both mounted about the same height, about 8 feet off the ground. So they're basically going to see similar things. So that's a good test to see if mobile LiDAR will work in a given situation. Rain, fog, standing water. Yeah, the lasers don't like water. Fog gives false returns from the air. We just won't scan in the rain, but we do see standing water occasionally when we scan, and we just know that there's a pond there, and that's something to be aware of. We had a project downtown Placerville. It was we detected where ponding was because it was there. It was pretty straightforward. Urban canyon, steep terrain. Again, that affects positioning. However, positioning can be remedied by more control on the ground, which I'll talk about again later. A good combination that we've done most recently with our acquisition of a heavy lift drone and the Regal VUX1 aerial mini laser scanner is we've done a couple projects probably 3 projects now for Yolo County, where we've scanned the roadway with the mobile system, and we flew up and down each right-of-way line with the VUX, produced a composite point cloud, went into extraction, and the data from one versus the other looks the same, just a little less density out of the air, but it's a good combination for fully saturating a corridor without putting boots on the ground on private property. Just fly just inside the right-of-way, and we get the coverage we need. So basically, in terms of cost, accuracy, density, the higher the accuracy, the higher the density, prices go up. So if you look at the lower right end, single pass for planning, some less accurate inventory, asset inventory, low density scan data, low accuracy as well. Prices are basically going to be lower. We could basically, what we would do is drive the project, process the trajectory based on a smart base, an Atlantic smart base solution, or we could set up a base station on a known. If we set up a base station on a known, but don't adjust to ground control, we find that the point cloud, in a reasonable GPS atmosphere is probably plus or minus 0.2 vertically, so it's pretty good. Horizontally, it's inside a tenth with good GPS. So that low accuracy and is a little bit better accuracy than what this graph is showing. But then we jump up into engineering surveys, pavement condition surveys, which we're starting to do more of with the scanner. Need high density, need high accuracy. So prices are driven by control primarily on that. There's a really good document out there. It's been out there for about 10 years now from the Missouri DOT, put together in conjunction with HDR and Sanborn. There's a link there at the bottom of the screen. Basically what they did is they took a 7-mile stretch of rural state highway in Missouri, and they actually did the survey using 5 different methods. Boots on the ground, aerial LiDAR, that's fixed wing aerial LiDAR, mobile LiDAR, static LiDAR, and then conventional aerial mapping. And this basically shows a breakdown of the man hours involved, labor costs, man days to get the work done, and then the key number is the cost per mile. Again, this was 10 years ago. We're probably more efficient these days. Could get by with a little bit less control, better extraction features. So I think, and then what's not factored into this capture is UAV LiDAR flying at about as low as possible with a high accuracy, high density UAV scanner. I'm impressed with what our guys are getting with the UAV system. But this is a pretty good comparison. If you get the handout or go back to review the presentation, you can get that, take that link or jot it down. It's really a good document. Again, it's 10 years old, so some of the pricing's a little dated, and then of course, in my opinion, efficiencies are a little dated too. So mobile LiDAR platforms, typically you see it mounted on a truck, such as this. This is our local scan vehicle here in Folsom. If the project is within a 2-day drive, we'll typically drive our vehicle and take the GPS equipment on board the truck. In the cases where we were traveling to the East Coast in Alaska, Australia, we have a Pelican crate where we crate up the scanner and ship it. It arrives. We also ship it with a set of Thule lumber racks that we can erect on virtually any pickup truck, on the bed of any pickup truck. I think I've got a photo of that later. We've mounted it to ATV, scanning along PG&E power lines. We had a rack manufactured for our bathymetric survey boat, so we can acquire simultaneous bathy data and landside mobile LiDAR data from the boat, and mount it to a high rail truck. And I'll show you a little bit more about this high rail truck a little bit later when we talk about the LA Underground project.
Hey, Joe, we did have a question come in.
Yep.
Do you want to address this now? I think it'll be timely.
I think we do them as they come, yeah.
Okay. With the improving survey technology of UAS, what surveying criteria should be considered when choosing UAS over mobile LiDAR? And that's from Chukau down in Southern California.
Yeah, that's a very good question. So accuracy is one consideration. We're not getting the UAV LiDAR as accurate as we are with the mobile. Probably half. We're probably 2 centimeters with the UAV. Probably maybe 1.5 centimeters even, with the right amount of control. So pavement accuracy would be one set of criteria. The other is how wide is the corridor to be mapped? Because as I say, there are limitations with the mobile system. It only sees what it sees. If it's grasses, that's all we're going to get, as opposed to the vertical perspective from a UAV with a survey grade LiDAR system. You're going to be bouncing pulses off the ground. Like I say, I'm really impressed with our UAV systems doing, and I think with the right amount of control, we can satisfy most accuracy needs on pavement, depending on who the client is. For example, Caltrans has a much higher pavement survey tolerance than the Iowa DOT. The Iowa DOT was interested in plus or minus 600. So we got away with a lot less control on our mobile projects in Iowa. But when we do combined mobile and UAV LiDAR, they use the same control. So the control, if you densify it for aerial, and the targets are slightly different too, and need a slightly different target to pick it out of the aerial scan or the UAV scan data, because the point density is less and you can't quite make the target out quite as well. So yeah, the considerations, to make a long story short, which it's too late for that, is is accuracy on hard surface, and then width of coverage and ground cover. That's a great question, though.
And we're also running into UAV issues around our airports. So proximity to sensitive airspace that you can't get a clearance into would be another one. And,
exactly.
Hey, all this talk about your LiDAR UAV, we're looking forward to a presentation on that next year in Reno.
I'll do it. Yeah.
So drop the hint there.
Keep me in mind. I'll do it. Yeah. Anytime a question pops up, Rob, just let me know. So mobile LiDAR applications, obviously, highway. This is what it looks like in Iowa and in the spring. Another Iowa project. See, I don't know if we scan this one at night or not. I don't have RGB on this point cloud. I do on this one. This is another Iowa DOT project. This was Tampa, Florida, Leroy Selman Expressway. Went out and scanned a design build project out there. This might look familiar to Sacramento area people. It's WX Freeway or Camellia City Viaduct. We scanned for Caltrans Division of Structures, I don't know, about six years ago. It was a really good project. Again, it's nice working with Caltrans, providing traffic control for setting the ground control points, arranging for the MAZEEP, running the traffic interference behind our scan vehicle. This project turned out really well. The intent of this project was to fill that void between eastbound and westbound 50. Turned out quite well. Bridges. This is a Grapevine project. So we drove I-5, obviously each direction a couple times. We also drove the crossing structure. So we basically shrink wrapped this bridge with a point cloud. So any way you twist it, you can take a measurement on that bridge. This was at Leroy Selman Expressway in Tampa, Florida, multi-level structure. There's yet another level down below that was scanned by our local survey prime. They scanned that terrestrially. They wanted a piece of the scan action, so they scanned all the surface streets from down below with their static scanners. Pretty cool to compare imagery to scan data. The imagery is imagery, but when you look at a point cloud, you just get a little more excited about seeing an image made up of hundreds of thousands or millions of points. Urban streets, downtown Roseville for a little project down we had with them. Anything that's out there is going to be in view, all the overheads. I mean, the scanners are indiscreet about what they pick up. This was a behemoth of a project. This is looking down on Market Street, San Francisco, right in the financial district. So talk about an urban canyon. We probably would have been better off just shutting the GPS receivers off because we were getting multipath. Basically, we're scanning in a canyon or a tunnel, but we had sufficient control on the ground to control this to the degree of accuracy that San Francisco was looking for. I believe we had ground control points every 250 feet on each side of Market Street. Another view, picked up all the buildings. This was probably the most detailed topographic survey we ever pulled together from anything. It was asset inventory to a high degree of accuracy, and they wanted connections to all the overhead. It was just an amazing amount of work to compile this 2.5 miles of Market Street. And there's you can see one of our LiDAR targets right there on the curb. We use chevrons for our LiDAR targets, but yeah, so basically every 250 feet, each side of the roadway, pair of targets. Aviation, this is the Calaveras County Airport, I'm pretty certain of. This is Cedar Rapids, Iowa Airport. What was nice about working with that local firm, or that Midwest-based firm, is they had projects for us to work, other projects for us to come out and provide scanning on while we were mobilized to pick up scans for the Iowa DOT. I think this is Calaveras County again, kind of a weird perspective on it. I feel like I'm upside down or something, but. And then this is Des Moines International Airport, where we collected our point cloud with imagery, so it's a colorized point cloud. As I mentioned earlier, we fabricated a rack for our larger bathy boat, Sacramento River I Street Bridge. We obviously collected the bathymetric data while we were scanning Old Sacramento and all the crossing bridges downtown.
And
just another view.
That bridge actually pivots, right?
Yes, it does. Yeah, that's the pivot bridge. Just a cross-section view of it. This is so we're starting to use it for pavement condition surveys. We can generate PCIs out of TopoDOT software with the good high density point cloud. But in this situation, this was a Caltrans project, District 1 up on I-5, Siskiyou Summit. I think it was about 8 miles of scanning. So what we see here is basically part of the deliverable, although I've highlighted the colors so they'll stand out better on the point cloud. Basically, this is a bridge on I-5, nice contours, basically extracted each lane line at a 10-foot vertice, dropped a random point every 10 feet along station, 3 feet across station to generate the DTM. And one of the ways we QC the DTM versus the scan data is display the point cloud and compare it to the contours. They should change color at the contours. And in this case, we're displaying 1/10 of a foot contours within the mobile LiDAR and 1 foot contours in the CAD file. And you can see that the change of color happens at the contour. Just up this was probably a relatively recently rehabilitated bridge, concrete as well. Further up the road, we had a situation like this. Point cloud, contours, not looking real pleasing to the eye. At the time, we hadn't delivered the point cloud to District 1 yet. We delivered the CAD file on the surface, and they immediately came back and said, "Man, there's something wrong with your brake lines up the roadway." these contours they can't be like that. So we sent them a cross section of the point cloud, which is the dashed line, and we drew a plane from edge of travelway to edge of travelway. Now the whole purpose of our mobile LiDAR exercise up on Siskiyou Summit was to map pavement rutting from tire chains, studded snow tires. This is an exaggerated cross section, but the depth of those ruts are exceeding 0.05 of a foot. So there's quite a bit of material missing from the roadway, and it creates that look of a contour. However, you'd never see it if we didn't do this with LiDAR, without LiDAR. Even 1/2 foot contour mapping from aerial or boots on the ground, you're going to pick up the edge of travelway, the lane line, and the edge of travelway, and it's going to triangulate across, and you're going to get nice smooth contours, which is not the case in this scenario. The value this adds is two things. Either knowing that there's so much material missing from a given cross section over the course of 10 miles, the contractor's concrete or pavement removal volumes are going to drop off. So there won't be the payment for his removal you can quantify with information such as this. Or if it's simply an overlay, and it's a 2-inch lift relative to, let's say, edge of travelway, the contractor's going to be putting a lot more pavement down than he anticipates to fill all those voids. So there's payoffs, trade-offs, whatever the case may be, whether we're scanning for a contractor or for the state. Each can benefit from mobile LiDAR in a situation like this. Rail application, which I'll talk more about later when we get into the LA Underground project. Mounting on a high rail truck. A lot of firms in the Midwest for positive train control projects are mounting their systems to actual railroad cars or moving Amway trains, basically collecting data while the train's going about its daily business. A lot of, again, positive train control, a lot of overhead acquisitions being done. This was a project we went out to Long Island, 18 miles of Long Island Railroad, scanned each direction, basically threading the needle between commuter trains, because as you imagine, coming from Long Island into the New York City area, those commuter trains run around the clock. They just run less frequently at night. So for the most part, we scanned at day. We were able to make one pass. I'm sorry, we scanned at night. We were able to make one pass between commuter trains to acquire imagery to colorize the point cloud. And then rail. This is part of my further presentation down the road. This is part of the LA Underground, scanning rail lines into the underground. One of the early on questions in using mobile LiDAR was, what are you going to give me out of it? Because I can't possibly use a point cloud. I don't have software. The data set's too large. So that was key to me when I first got into this, was developing products that end users are accustomed to using. The same DWG or DGN format, a TIN, or is it an inroads DTM? Basically taking this much data, and I don't mean dumbing it down in that sense. I mean just filtering it down to a manageable level, but still taking advantage of the density and the accuracy of the data. So that's when I was talking about that earlier project where I talked about 10-foot interval on brake line vertices, dropping road points every 10 feet along station and 3 feet across the roadway. Essentially what that does for us is it gives us, it'll indicate if there's rutting, if we can get roadway points or brake lines where the wheel tracks are. It'll tell us if there's any kind of rutting at all. But basically, yeah, extracting 3D feature lines, using Basically, we use TopoDOT software exclusively. We're working in real time. We're drafting the 3D map in MicroStation. So we're not compiling shape files in a software that we're going to turn around and import those shape files and format them in MicroStation or AutoCAD. We're drawing real-time CAD deliverable by level, by layer if we're working in a DWG seed file. We're drafting in real time. If we need to make an edit, we're editing in real time. We don't have to go back and export a new shape file, import it, and then bring it into the mesh. Basically overlaying aerial imagery. There's the DTM. In this case, we didn't anticipate. I think they were going to rehab the road, so we didn't go to the exercise of dropping road points across the lanes. So it all boils down to what the end user and end deliverable are in terms of what's extracted, but basically delivering it to the client, the in-house designers, the engineers in a format they're accustomed to using, and not scaring them with this point cloud, black box point cloud that we're preparing. A lot of the work I should say a lot of the work we did with Iowa DOT was just delivering point clouds there, and actually we're delivering pod files, the Bentley format for a point cloud. Their designers are designing right on the point cloud. They can cut cross sections, they can pan around, they can. A lot of it was ADA work where they can pick their own pavement elevations or sidewalk or curb returns. And do real-time design on a point cloud for ADA ramps. That was that was our primary deliverable for ADA surveys to the Iowa DOT.
Joe, Cynthia asked, how long does it take to process that detailed topo? That was from a few minutes ago. I responded to her, it all depends on how much has to be extracted. But the processing or registration aligns the scan data to the control, and that could take a day or two. And then checking the registration of the validation targets afterwards, and then the extraction of all the topo data. Pack a lunch, right? I mean, this could be weeks on end of extracting topo, but probably a day or two for registration.
Yeah. So, mobile LiDAR, the survey grade mobile LiDAR systems are pretty expensive. And, I've been asked several times, is your system paid for itself yet? We probably paid for it by now, based on it's our own recovery rate, the rate we charge for usage. But what's difficult to quantify is the number of labor hours that this system has generated that we wouldn't have had we not had this system. So it's generated quite a bit of labor hours. Now, we can acquire 20 miles of Interstate 5 in a day with no problem. And we're going to probably spend about 4 to 5 days per mile extracting the topographic survey to download, process, adjust, and export the point cloud before we do extraction. That could be smaller projects, a day and a half, larger projects up to 4 days, maybe 5 days, depending on the size of the project. But basically, for the most part, we for estimating purposes, we estimate 1,000 feet to a quarter mile per day, depending on the detail that's needed. Is this roadway going to be blown out and a new one put in? We don't need the detail. Are we matching pavement grades on the inside shoulders and extending slopes? We need a little more detail. So knowing those types of things going in help us develop a better cost estimate. But quarter mile a day is pretty aggressive. 1,000 feet a day is relatively safe. It goes pretty fast. If the striping on the pavement is in pretty good condition, we have good reflectancy. We could do auto extraction of striping, and then to enhance the DTM, basically copy those lines parallel, drape them to the point cloud. Now it's a brake line on the roadway. So there's a lot of different things that are becoming more and more automated that are helping us be more efficient in the extraction. The deliverables. All right, so now I'll get into the project. So what happened is I put this presentation together a year ago, and I delivered it at the International LiDAR Mapping Forum, and I had a 20-minute slot. So when I asked if I could present at this conference in Las Vegas in March, I indicated I can't fill 90 minutes. There's no way I can extend a 20-minute presentation to 90. So what I did is what Chrissy did is found someone to share my slot. That was in March, but now I'm not sharing a slot with anyone. So I said, man, how am I going to extend 20 minutes to 90? So I added everything you've seen up to now. I added to this just in order to burn as much of your time as I can. So I think we're doing okay. I got plenty of time to get this in, but anyway, it was a good background on mobile LiDAR. And now let's get into this project in Los Angeles.
Sounds great, Joe.
Metro is the client. T.Y. Lin was the prime. Wagner Engineering Surveying was their surveyor, and Wagner Engineering contracted with us for the mobile scan. And this little video is going to fly us through the project, showing what's going on down there. Just an unbelievable amount of work underground. Union Station, there's part of the portal we scanned. We scanned some of this rail yard. There's one of the tubes. We scanned the rail yard twice. We did a portion of it in 2017, another portion late 2018, and then we scanned into this portal and then about 1,900 feet into Union Station. And then the iconic bridges over the Los Angeles River. Man, it's pretty cool to see all that stuff and be right there. And the coolest part is yet to come, the data that was produced for the project. So again, 2017, we came down, we mapped these portions of the Division 20 yard. They were going to rearrange some rail for quicker turnaround of the commuter trains that popped out of the portal, which is off to the right of the screen right now. Oh, I'm sorry, not off to the right of the screen. The portal is right here. And then Union Station is up here. Came back in late 2018, expanded on the rail yard scanning, including the portal and scanning of the twin tunnels. Here's the portal where we go underground. So the depressed rail starts back here, goes underground, and into Union Station.
Hey, Joe, it looks like the tracks get, maybe a crossover down in the lower left and then a possible crossover there up to the upper right.
Yeah,
right there.
There is a crossover, and this is definitely a crossover. I don't think that's a crossover. This is kind of cartoonish right now. I don't believe that was a. Yeah, that's a good question, Rob. I don't believe that's a crossover, but it could just be the line weight bleeding together in CAD. There was a location where the tubes did come together for a man passage.
Oh, that could be that spot then.
Yeah. A Metro high rail truck. our first choice for doing any rail scanning is to use a high rail truck from the rail operator, because typically they'll require one of their personnel to be the driver, and then as well as a person on the radio in touch with the yard control. So Metro made their F350 available to us. And those are the portable racks that we ship, or in this case, we drove down to Los Angeles, erected them on their truck with the scanner. Did that in the morning, and then later, I think we did a nighttime scan just because of rail traffic. It was going to be too dark in the tunnel for imagery anyway, so it was a nighttime rail scan. So the challenge was delivering survey grade mobile LiDAR based mapping for 1,900 feet of twin 18-foot diameter subterranean tunnels with zero GPS. I know a fellow in Spain who has a Regal scanner. He did a similar project, and we kind of, based on his success, learning and successes, we were able to recreate that on our project. There's the twin tunnels, yeah, 2 of them. I'll talk more about how we. I'll talk more about how we scanned them in a moment. So Rob, here's the trajectory lines, the white lines. So yeah, those 2 trajectories just came close together where the man passage was. So those are the actual trajectory lines we drove into the into the portal and into the tunnel. The yellow dots represent control. Basically, up where we had good GPS sky, we set control points between the sets of rail visible from each pass. And then as we started dropping down into the portal, we densified the control. Basically what we did is we set our typical chevron LiDAR target on the walls of the portal and of the tunnel, approximately every 200 feet. And opposite each one of these was a traverse point. Wagner ran a conventional traverse and set a control point between the rail, side shot, and then move on and do the same 200 feet later. This would be the control point between the rail. Here's the targeted point on the wall. So basically, when we adjusted the scan data, we adjusted the scan data to the targeted control point on the wall where we saw the chevron. We were able to grab the point cloud representation of the chevron and assign it to, in this case, point number 5040. That's how we adjusted the scan data. What we did after the fact, and I'll show a report of that later, was TopoDOT has a very nice tool for assessing the accuracy of the point cloud at an XYZ position. We ran that report against the traverse points on the floor, and I'll show you the results of that later. So to scan this, again, redundancy is as critical as control. We scanned each tube twice. And basically we had to drive in the tube to Union Station, stop, back out, and then do it again in each tube. We only scanned on the inbound. The software, we were pretty certain the software would not handle us going in reverse with the scanners acquiring data. So we didn't even bother testing it, knowing we were going to be driving each tube twice at about 5 miles an hour. What it produced, what you see there, points per square meter density, was just off the chain high. 17,000 points per square meter on the ceiling. That's because the scanner was 4 feet away from the ceiling. 4 to 6 feet away, and then 10,000 points per square meter on the floor of each tube. When we started the scan data adjustment, this is the first adjustment applied to the trajectory based on the first iteration of cloud-to-cloud adjustment. So what it's showing is we've got cloud mismatching on the magnitude of 1.4 meters in the across track. So we were losing our heading. What's really surprising is the height that the IMU maintained without GPS lock. So this is the first pass into the first tunnel. Drove in, backed out. We got back out into good sky, regained initialization on all the systems. This was the second pass in the first tunnel. Same thing, came out. Actually, this is a lot of a longer duration because we had to switch tracks. First pass of the second tunnel, things were drifting a different direction in a long track in this case. But what amazes me is how tight the height held in there throughout the whole GPS outage. And then this was the last pass in and out. Corrections to the trajectory and roll pitch and heading. The yaw probably is indicative of the cross track. So there's some pretty good corrections taking place between the multiple passes on the first iteration of cloud-to-cloud adjustment. Corrections after that pass, the residuals were we're still half a meter off in a long track a cross track height 9 centimeters. I can't believe that without any GPS positioning. Then so usually we run 3-4 iterations of cloud to cloud. You get to the point of diminishing returns. So you just once you get these down inside a centimeter, it's like you're just killing time now, and it's really not really helping you out. In the final adjustment, I still haven't figured out why we had this anomalous spike right here. It really didn't. I'm not sure what that was from. But in any case, if we were to zoom in on this, the corrections applied were down in the centimeter range to the corrections applied in all respects. Rather than correcting tenths of degrees on the trajectory, we're down to hundreds of or thousands of degrees. So the trajectory pulled in quite nicely after the cloud to cloud, and then the type lane adjustment. And then this was the final adjustment applied to the trajectory before we exported the point cloud. Height, we're down at a couple millimeters, 2 centimeters on the cross track, and then the long track. This was the final adjustment, again, applied to the trajectory for the final point cloud.
That's looking pretty tight.
Pretty tight. Yeah. We got the guy that does our scan acquisition and processing adjustment, Tom Cade, is like a wizard, and he's been a resource to the folks at Regal North America a number of times. He's developed some methods that I'm not sure how many other Regal users are doing, but I have not seen a data set come out of Tom's workstation that was not as good as this data right here. So in looking at the point cloud itself, cutting cross section through the tube with the control point superimposed, that's along the wall. The differentiated point clouds are the two passes. So they adjusted together quite nicely. They adjusted to the control point quite nicely. The thickness of this point cloud at this location is probably about, I'm guessing about 3 to 400ths. It ranges 2 to 500ths, but this was a pretty tight data set. So we plant the average thickness of the point cloud right on the control point, and that's why we see what we see here. The point cloud data through these two tubes were strictly tied to these points on the visible points on the sidewall. So when we compare the traverse point on the floor, this is what we're seeing. We didn't use this point in the adjustment, but it helped us with our final QC. You see, it's not quite as tight in the middle, but if that's 3 or 4 hundredths and you take the mean, it might be off 1/100th of a foot in a no GPS atmosphere. That's what the point cloud looks like superimposed on the control point. So basically, Regal has automated, I'm sure the other software application, LiDAR point cloud adjusting softwares do too. You can build a template for your target and it'll find your target and orient it to your control point. But Tom's still old school. He likes to see the target and make sure it's doing what he wants it to do and not just relying on what the software wants to do. So this is how the reflectancy of our chevron related to the XYZ of that target on the wall. The TopoDOT adjustment tool, or scan data analysis tool, where we compare the point cloud. We compared the point cloud along the floor of each tube to the QC points or the traverse points along the floor, and we generated our MSE in that point cloud of 18 thousandths of a foot throughout. I was looking at this the other day, and if a guy wanted to get real crazy about things, we could have applied a vertical boot to this and raised it 11 thousandths of a foot to equalize to mean out the low and the high. But I mean, we're just splitting hairs there, and we're just fooling ourselves if we think we're going to really make this any more accurate than what we've got it. The deliverables were 3D microstation files and En-ROADS DTMs. Again, we used TopoDOT to extract the features that were requested. We generated a DGN and a DTM two for the one on the bottom half of the tunnel, one on the top half, not knowing how TY Lin was going to use the DGNs or the DTMs at their end. So we just basically gave them a top half and a bottom half. Point cloud at the portal, superimposed line work. They wanted top of rail. They wanted stairways. They wanted basically items of clearance concern. Steps down below. They did want to know. I'm not sure if they're going to reconfigure these catwalks, because they did want this. They wanted to know about the utility that was beneath them, handrails, utilities running up the sides of the tunnel, switches. Picked up the stairway. There's the cavity for that utility. We actually meshed the tube to generate the En-ROADS DTMs on the top and the bottom. Extracted this center line of rail and a profile. Also develops the amount of cant from at the extraction interval, cant on the rail. So that's basically, that was the end deliverable, what you see right here to TY Lin, including the En-ROADS DTMs. This is looking back at the Division 20 yard. This is some of the extraction work we did back in the yard. This is like the 4th Street Bridge crossing. So basically, like I said earlier, delivering products to the designers that they're accustomed to using. We can, and again, we deliver the LAS format, pod format for the Bentley users if they have designers that want to get into the point cloud themselves and pull additional information out, or PCG format for Autodesk projects. Again, I'm getting right at the end of this thing. The challenge was to deliver surveyed grade mapping in these twin tunnels, and we were pleasantly surprised with the accuracy of the data. The deliverable itself, we knew we could produce a quality DGN and DTM, but it was all going to be based on the point cloud that we produced, and we produced a point cloud that exceeded our expectation on this project. And basically, that's all I've got.